Hello everyone, welcome to this channel. If you're new here, my name is Hasan. Let's begin our 11th part of the video series. I hope you're enjoying this video series with all those beautiful fancy notes and colors. In this video, I'll be discussing about critical angle, and then I will be following that concept with total internal reflection. So it's an easy topic and you'll see the concepts are very easy. Mostly in NEET, they will ask questions directly based on the formulas from critical angle and total internal reflection. So if you just understand the concept and just grab the formula, then you can solve most of the questions asked in NEET. But I'll be giving some tricky questions and formulas so that you can solve if they ask any tricky question in exam. So just follow on with the lecture and you'll see things are very clear and easy. So I will discuss some tricky questions from this part and you're good to go. So let's move on and start our video. But before that, let's roll the intro. Okay, now let's look into the concept of critical angle. This is very easy. So let's concentrate. If you look into this diagram, then we will see that I have taken three rays, like ray number 1, 2, and 3. Okay, now one thing you need to understand is that the rays should go from denser to rarer medium. So this is the denser medium, this is the rarer medium, and the rays are going from denser medium towards the rarer medium. Then only we'll get the critical angle. So this is very important. Now what we are actually doing is, see, this is angle of incidence for the blue ray. Okay, so once it goes into the rarer medium, we got the angle of refraction as this one, isn't it? Now if you just look into our second ray, that is the pink color ray, then what we'll get is that we have increased the angle of incidence now to I. Okay, and we got an increased angle of refraction R, isn't it? So as we increase the angle of incidence, we are getting a bigger value of angle of refraction. Now looking into our third one, this is our angle of incidence. Now I have increased the angle of incidence to a more bigger value. Now as I am increasing the angle of incidence, what happens is angle of refraction is going on increasing, and a time will come when the angle of refraction on the rarer side will be 90 degree. This is the angle of refraction. So when the angle of refraction becomes 90 degree, then we say that critical angle or the angle of incidence is the critical angle. So let's define what is critical angle now, and then I will explain why it is known as critical. Okay, first of all, understand the definition. The definition says the angle of incidence while moving from denser to rarer medium. This is very important. The angle of incidence while moving from denser to rarer medium, for which the angle of refraction in the rarer medium is 90 degree. So you can see 90 degree is in the rarer medium. That is the angle of refraction. Okay, and this angle of incidence is known as the critical angle in that case. Okay, so critical angle is denoted by C, and basically it is a special kind of angle of incidence. This is all about the definition and the concept of critical angle. I hope this is clear. Now let's move into the concept of why it is known as critical angle and what will happen if the angle of incidence is greater than critical angle. Okay, critical angle, why it is known as critical angle is very simple. Anything in physics is known as critical when it is like the threshold of something. That is, it is the boundary of something. Then we say that boundary as critical or sometimes threshold. Okay, so this angle of incidence is known as critical angle because once it crosses this critical angle, then things will change, because that's the final boundary or the final threshold. Okay, so if angle of incidence is greater than critical angle, then what will happen? Let's look into that. So what we have done, if you look into this diagram, then we can see that this blue color is the angle of incidence for which the angle of refraction is 90 degree, isn't it? Therefore this angle of incidence is known as critical angle from the definition, isn't it? Now what we have done, we have taken another ray, that is green color, and we have made the angle of incidence greater than the critical angle. As you can see here, this is greater than the critical angle. Now we can see that the rays doesn't refract and go into the rarer medium, but rather it reflects back into the same medium, that is the denser medium. And we can see the phenomena of refraction is no more there, and the phenomena of refraction got totally converted into the phenomena of reflection. So let's understand this. If angle of incidence is greater than critical angle, then there will be two things. That is, there will be no refraction, and number two, there will be a reflection which is known as total internal reflection. So this is a special kind of reflection known as total internal reflection. Since this is a kind of reflection, therefore it will follow all the laws of reflection. As we have learned the laws of reflection in my earlier videos, so it will follow all those laws. Okay, and one of the major law that we have learned in law of reflection is that the angle of incidence will be equal to angle of reflection. Now if I draw it here, if this is the angle of incidence, then this is actually the incident angle, and since this is the reflected ray, as you can see in the diagram, then this will be the angle of reflection. Therefore we can say this angle of incidence should be equal to angle of reflection according to the law of reflection, isn't it? So this will hold true for total internal reflection. Now why it is known as total internal reflection? It's simple. Let's understand that. It is known as total because almost 100% of light gets reflected. Now 100% of the light doesn't get reflected, but almost 100% of the light gets reflected. Okay, in normal reflection, like when you're seeing yourself in a plain mirror, then the kind of reflection that we get is not 100%. Okay, maybe 80%, 70%, depending on the kind of material used. But in case of total internal reflection, 100% of the light gets reflected, and the image that are produced due to total internal reflection is very, very shiny and clear. The reason is that 100% of light gets reflected, almost 100%. Okay, now let's look into why it is known as internal. It's known as internal because reflection occurs internally. Now if you look into this diagram, you'll see that the rays are going from the denser into the rarer medium, but instead of going outside into the rarer medium, it reflects back inside the denser medium only. So everything is happening internally. Therefore this kind of reflection is known as internal reflection. Now why it is known as reflection? Because it follows the laws of reflection. Therefore the total phenomena is known as total internal reflection. I hope this is clear. Now let's draw a summary of what I have told and let's wrap up the concept. Okay, so the summary for what I've told so far about total internal reflection is that these are the conditions of total internal reflection. That is, number one, rays should move from denser to rarer medium. Simple. And number two, angle of incidence should be greater than critical angle. Now what will happen? There are three cases. If angle of incidence is less than critical angle, then what will happen? Very simple. Then it will show refraction. Simple as that. Okay, if angle of incidence is equal to critical angle, then it will show grazing emergence. Now what is grazing emergence? Let me explain. So let's look into the figure again. Oh, the figure is very untidy. Let me draw it here. Okay, let me draw it here. This is our denser medium mu2 and this is our rarer medium mu1. So I'm trying to say grazing emergence means if the angle of incidence is the critical angle, then what will happen is after a refraction it will graze the interface. Okay, like this. That is, the angle of refraction will be 90 degree. This kind of emergence is known as grazing emergence. So this is clear. Now the last one, if angle of incidence is greater than critical angle, then it will show total internal reflection, and this is very easy, as I have told and showed in the figure, that if the angle of incidence is greater than the critical angle, this one, then it will reflect back into the same medium. This phenomena is total internal reflection. As you can see, the angle of incidence is greater than the critical angle. So this is all about critical angle and total internal reflection, the concept, the core concept of this. Now we will move into the concept of measuring critical angle. Okay, this is very important and questions are very frequently asked from this topic. So let's move on and see how to measure critical angle. Okay. Now let's see how to measure critical angle. It's very simple. See, for critical angle to occur or total internal reflection to occur, we know that rays should go from denser medium to rarer medium. Now look into this figure and we'll see that we have two medium, that is a medium 2 and medium 1, having refractive index mu2 and mu1 respectively. Now since rays is going from this medium, so in order to obtain critical angle, this medium should be a denser medium and this medium should be rarer medium. Okay, so we can say that mu2 is greater than mu1 because we know denser the medium, more is the value of refractive index. This has already been established in our previous videos. Okay, once you've understood this, since we are measuring critical angle, so what we will do, we will see the angle of incidence for which the angle of refraction is 90 degree. Okay, since this is the angle of incidence for which the angle of refraction is 90 degree, we can say that this angle of incidence is nothing but critical angle. Simple as that. Once you understood this, now what we'll do, in order to find the critical angle, that is this angle, we will apply Snell's law. Now how to apply Snell's law? Now don't memorize this, that mu is equal to sine I by sine R. Okay, this is also Snell's law, but I have seen students confusing this. Like, if you remember Snell's law is mu is equal to sine I by sine R, then what happens is you are forgetting this is the mu of which medium, whether it is mu2 or mu1, and you start confusing yourself. Okay, this is easy for me. I can explain this is refractive index of which medium. This is easy, but I have seen students confusing. So what I say to them is that instead of remembering this formula, just try to remember this formula. This is much easier to remember. How? Let's explain. See, mu2 sine I is equal to mu1 sine R. How to remember this? Take the refractive index of the medium. Suppose we are taking the refractive index of the medium 2, then we will take the angle produced in medium 2, and we can see the angle produced in medium 2 is I. Now when we take the refractive index in medium 1, then we will take the angle produced in medium 1. So here we can see it is the angle 90 degree in the medium 1. So this is how you apply Snell's law without any confusion. So we have applied this, then we got this, that is sine I. We know this is the critical angle because the angle of refraction here is 90 degree. So we just replace the value there, and we got that sine C is equal to mu1 by mu2. This is the formula you need to remember. And I've seen students confusing this, like sine C is equal to mu1 by mu2. Okay, and mu1 and mu2 is given, but they will never specify which one is mu1 and which one is mu2. And I've seen students confusing. So how to memorize this? Let's see. We know sine C, the value of sine always lies between -1 to +1. We know that sine theta is between +1 and -1, and you know the curve. Okay, so here we'll be dealing with, see, we are dealing with angle of incidence here. Okay, this theta is actually angle of incidence. Now angle of incidence can be 0 and can move to 90 degree. Okay, so from 0 to 90 degree it can move. So this theta can have value from 0 degree to 90 degree. So if it is 0 degree, then sine 0 is 0. Therefore you can say the sine of angle of incidence values lies between 0, that is sine of 0 is 0, and maximum it can have sine of 90 degree is 1. Okay, but we know that critical angle can never be 90 degree. It is always less than 90 degree. Therefore you can say that sine C's value is always less than 1. Okay, sine C's value will be always less than 1. Now for anything to be less than 1, we know sine C is equal to mu divided by mu. Now it can be mu1 by mu2. So it is actually a division. Now this value will always be less than 1, and we know for a division the value is always less than 1 when the lower part value is greater than the upper value, isn't it? If the lower value is greater than the upper value, then this will always be less than 1. So always remember that refractive index sine C, mu by mu. How to remember? See, the lower part should be greater because we know sine C is always less than 1. So we know the mu of denser medium is always greater than mu of rarer medium. So mu of denser, and this is mu of rarer. You can remember it in this way. So sine C is refractive index of rarer divided by refractive index of denser. If you just remember it in this way, then you'll never get confused as a student. And I've seen students making a lot of mistake here. From experience, I'm saying this. Okay, use this concept and it will be easy for you. Now let's look into one of the example and things will be much more clear. Now if the question is like this, find the critical angle of diamond in air. Okay, we know air is the rarer medium because the refractive index of air is always the least. So if this is the question and need to find the critical angle, then we can directly say that sine C, which is mu of rarer by mu of denser. Now you will never confuse. Now rarer is which of the two medium, air or diamond? Obviously air is the rarer medium, so we know refractive index of air is 1, and mu of diamond, it will be given in your question. Okay, so if it is given in your question, then you can easily find C, that is C will be equal to sine inverse of 1 by refractive index of diamond. This is how you calculate critical angle. So simple as that. Remember that sine C, where C is the critical angle, is equal to refractive index of rarer medium divided by refractive index of denser medium, and the value of sine C will always be less than 1. This is how you need to remember. I hope the concept is clear. Okay, now let's look into some of the trickier problems from this part, because see, the easier problem I won't show because most of the problem here will be formula based. If you know the formula, you can easily find the answer, but I'll show you some of the trickier problems so that when those kind of questions are asked in the exam, then you can easily smash those and you'll get the marks. Okay, and it will help to polish your concept also. So let's do that. Okay, now let's look into this question. This is a bit tricky question, so I will request you to concentrate here. Okay, so let's see. It says, for a given incident ray as shown in the figure, the condition of total internal reflection of the ray will be satisfied if the refractive index of the block will be. Now, this was asked in the year 2002. The question is very simple. It says that what will be the refractive index of this material or the slab so that this ray, the ray that you can see, this one, this ray undergoes total internal reflection. How to solve this? Let's see. For total internal reflection to take place, this theta should be greater than critical angle, that is theta c, isn't it? So let's consider that theta is equal to theta c. So let's consider this so that if we can find the critical angle, then it's easy for us to find the condition of total internal reflection. Okay, so let's see. If this theta is critical angle theta c, then we know that sine theta c, this formula has already been derived earlier. Sine theta c is refractive index of rarer by refractive index of denser, isn't it? Now rarer, this part is actually air, so we know refractive index of air is 1 and refractive index of the denser medium is given to be mu. Okay, so we got that sine theta c is equal to 1 by mu. Simple as that. This is our equation. But the problem here is that we cannot solve the value of mu from this because we don't know the value of theta c as well as we don't know mu. So there are two unknowns and a single equation. We know in mathematics, in order to solve two unknowns, we require two equations. So we need another equation to solve this, okay, because we have two unknowns. So if this is the first equation, how can we find the second equation? In order to find the second equation, we'll be taking into account this concept, the concept of refraction here. Okay, so if we use this concept, then we know that mu, refractive index of the material, is equal to sine 45 degree by sine r. This is basically Snell's law. So we can write that our mu is equal to sine 45 is 1 by root 2 and sine r. This is our second equation. Okay, so we can see that even then we cannot solve the equation because let's look into our equation 1. This is unknown, this part is unknown, and in the second equation this is same mu, so we will not consider that. And sine r, this is again a different unknown, so we have two equation and three unknown, so again it's very difficult to solve. So how to solve this equation? The problem here is we need to find out some way in order to replace this sine r in terms of theta c. If we can do that, then we will get two equation and two unknown. I hope this much is clear. See, the concept of physics is complete here, like equation 1 and equation 2. This thing what I'm talking about is actually the concept of math. Okay, so let's see, is there any relationship between r and theta? Obviously there is a relationship. See, if this is theta, then this has to be theta, alternate angle. If this is theta, then we know that r is equal to 90 degree minus theta. So simple. Actually we are taking this as theta, this theta c. Okay, so we can say that mu is equal to 1 by root 2. Now sine of 90 degree minus theta. If you solve this, then we are going to get mu is equal to 1 by root 2. Sine 90 minus theta is actually cos theta. Okay, so we got this. Now if you further solve, then we are going to get that if we solve it here, then we can say that cos theta is equal to 1 by root 2 mu. Okay, now we know that this is cos theta and the first equation is sine theta. Is there any relationship between sine theta and cos theta? Absolutely there is a relationship. That is square root of 1 minus cos square theta is what? Is actually sine theta, is equal to, this can be written as, see, we have squared this term, so this will be 1 by 2 mu square, then minus and 1 here, and then square root. This is nothing but sine theta, and we can write this in this way. Okay, this is derived from our second equation. So we got sine theta is this and we got sine theta is this. Now we can easily solve mu. See, this is unknown and mu is unknown. Here again sine theta unknown and mu is unknown. So actually we are getting two equation and two unknowns. So you can easily solve this according to mathematics. Okay, so let's rub this part and solve it here. Now therefore if we compare equation 1 and 2, we can write 1 by mu is equal to square root of 1 minus 1 by 2 mu square. Therefore we can write 1 by mu square is equal to 1 minus 1 by 2 mu square. Or if you go on solving this, then we will get 1 minus mu square by mu square is equal to minus 1 by 2 mu square. Okay, so mu square got cancelled and we got that 2 minus 2 mu square is equal to minus 1, or 3 by 2 root over is equal to mu. So we got that mu is equal to root over 3 by 2. Let me write it here. Therefore we got mu is equal to root over 3 by 2. Now let's understand. This refractive index that we got of this material as root over 3 by 2, if this is the refractive index, then we have taken this as, let's consider theta is equal to theta c. That means we are taking the consideration that this theta is actually critical angle, isn't it, at the start. Therefore if this refractive index is root 3 by 2, therefore this ray, look into this figure, this ray after refraction will graze through this interface. Why? Because we have taken this theta as theta c, isn't it, and we got this refractive index. So what will be the refractive index of the material so that this will undergo total internal reflection? Because you can see that this is not total internal reflection. Okay, now let me explain the concept. We know that sine theta c is equal to, we have got 1 by mu. If you look carefully, then we can see that refractive index and sine theta c is inversely proportional. Okay, let me explain this thing here. Therefore we saw that sine theta c is inversely proportional to mu, or we can say that if refractive index is increased, then sine theta c will decrease, which suggests that theta c will decrease, isn't it? This is the concept that we are getting from the equation. If you understand this, then things are simple. Now what we will do, if we increase this refractive index of this material, like we got this mu is equal to root 3 by 2, isn't it? So if we increase this refractive index, then what will happen? Then obviously theta c will decrease. Now let me draw it here. Now this is the normal, okay, and this is mu1, this is mu2. Now if we, now this is the critical angle, suppose theta c, and the incident ray, let me pick another color. If we put this, the incident ray, then we know that the ray will graze this interface, isn't it? Now what we did is we increased this refractive index. We have changed nothing. We have increased this refractive index, as a result of which we know from this concept that if we increase the refractive index, then theta c will decrease. So now the theta c is this much. Why? Because theta c will automatically decrease. Now we can see the same incident ray is now greater than the critical angle. Therefore it will undergo total internal reflection, isn't it? Therefore we can say that for this ray to undergo total internal reflection, this pink ray in this block diagram, if this ray has to undergo total internal reflection, then mu should be greater than root 3 by 2. This should be your answer. Okay, so if refractive index, see, refractive index is equal to root 3 by 2, it is the condition of critical angle, that is grazing emergence. So if we increase the refractive index more than root 3 by 2, then that theta, this angle of incidence theta, will undergo total internal reflection. I hope this much is clear. This is a bit tricky question and it has some mathematical concept embedded in it. I hope the concept is clear. But I'll show you a trick. If you can remember the formula, then you can solve this question within 5 to 10 seconds. So let's look into my trick. So the trick is, just remember, since this is a very common question, okay, this is very common. Whenever a question is asked like this angle is angle of incidence, and then this is angle of refraction, then this is theta, then what should be this mu, the refractive index of this material, so that this undergo total internal reflection. Okay, so this is such a common question that I tell my students to remember this formula, so that whenever this kind of question comes, then you can easily use this formula and find the result. So the formula for this is mu square minus 1 should be greater than sine square I. Just remember this formula and you'll get the result. Now in the earlier case, now in the question it is given that I is equal to 45 degree, isn't it? Now just put it here, mu square minus 1 is greater than sine square 45 is 1 by root 2 square, that is half, or we can say that mu is greater than half plus 1 is 3 by 2 square root. See, we got the result. So just use this formula and you will get this result within 5 to 10 seconds. I hope the concept is clear. Now let's move on to our second numerical. Now let's look into this question. It says that the critical angle theta c for light going from medium 1 to medium 2 is theta. So the critical angle is given to be theta. The speed of light in medium 1 is v. Then the speed of light in medium 2 will be how much? That's the question. So let's draw the scenario and then things will be easy. So this is our scenario, that this is suppose medium 1 having refractive index mu1, and this is our medium 2 having refractive index mu2. Okay, so this is medium 2 and this is medium 1. This is our normal. So the question is that the angle of critical angle is theta c, okay, and it's given that theta c is actually theta. So the refraction will be in this way, grazing emergence. Therefore, we can say the refracting angle will be 90 degree. So this is the scenario. Now it says the speed of light in medium 1 is v. So the velocity in medium 1 is v. So what will be the velocity in the second medium? This is the question. Now let's use the concept of critical angle, that is sine theta c, or theta c is given as theta, is equal to rarer refractive index of the rarer medium divided by refractive index of denser medium. Now refractive index of the rarer medium is mu2 and refractive index of the denser medium is mu1. Since light is traveling from denser medium to rarer medium for critical angle, we know this. So we use that concept, even though it's not given, we know it, that mu1 is greater than mu2. Sine theta is equal to, now earlier when we started the concept of refraction, I have said that there is a relationship between refractive index and velocity, and I said that refractive index is inversely proportional to velocity. You can check that lecture there, okay, and I have derived this mu2 by mu1 there. Therefore we can say mu2 by mu1 can also be written as v1 by v2, isn't it? Now we need to find the value of v2, velocity in the second medium, or we can say that v2 is equal to v1, velocity in medium 1, divided by sine theta, and we know the velocity in medium 1 is v, it is given in the question, by sine theta. Therefore the velocity in the second medium we got as v divided by sine theta. I hope the concept is clear. This is very simple. Since I haven't taught the concept of velocity in critical angle, so I gave this question in order to help you understand the concept of velocity that is linked with critical angle. Okay, I hope the concept is clear. Now let's move on to our next concept. Now let's look into this concept. I won't be giving a numerical based on this. I'll just give the formula, because if you know the formula, you can solve these questions very easily. So you just need to remember this formula. Let's see how to derive that formula. The question is concept of finding area of illumination. Now what I'm trying to say is that if this is suppose liquid, okay, and this is air and this is liquid medium, and a source of light is kept here, this is source of light, okay, then we can see that there is a specific area, circular area, that gets illuminated and the rest of the area doesn't get illuminated. Now why is this? So this is the part which gets illuminated, okay. So we need to find out the area of illumination. We need to find that area. So how to do that? Now let's understand the diagram first. This part gets illuminated because rays from bottom hits the interface and they enter into the second medium or air medium, okay, and we know that air is optically rarer, therefore we can see that it bends away from the normal. So as we go on increasing the angle of incidence in the liquid medium, the angle of refraction will go on increasing, isn't it? Then a time comes when this angle of incidence becomes equal to critical angle, that is theta c, then the light will just move in this way, that is grazing emergence. Okay, and after this, any light that goes past critical angle will undergo total internal reflection. That means no rays will go from this part into the air region or the second medium, so there will be no illumination there. The same thing is happening on this side too. So this side is actually, this angle is actually theta c, that is the critical angle. I hope this much is clear. If this much is clear, then let me rub this off. So now the concept is clear why we are getting the illumination area. So let me draw it again. That means this angle of incidence is critical angle. If this is critical angle, then we can say that sine theta c is actually refractive index of air, that is rarer medium by refractive index of the liquid, or we can directly say that air is 1 and mu of liquid, let it be mu. Okay, therefore we can say that sine theta c is equal to 1 by mu, where mu is the refractive index of the liquid. Simple as that. Once this is clear, we need to understand what sine theta actually means in mathematics. What is sine theta? Sine theta is basically a trigonometric ratio. Okay, so we know that sine theta for a right angle triangle is the ratio of perpendicular by hypotenuse, isn't it? So we can draw this triangle, sine theta triangle, like this. If this is theta, okay, this is theta c, then this is 1 and the hypotenuse is mu. Therefore the base will be, from Pythagoras theorem, mu square, square root of mu square minus 1, isn't it? I hope this much is clear. Therefore we can say that tan theta c is equal to 1 by square root of mu square minus 1, because we know that tan theta is equal to perpendicular by base, which is written here. Okay, that is perpendicular is 1 and the base is square root of mu square minus 1. So this is clear. Once this is clear, now you may be thinking why I have found out tan theta c. Now things will be clear. Look into this figure. Then if this is theta c, then this has to be theta c, interior alternate angle. Simple. If this is theta c, then this is the radius of the circle. So we can say that this is r, and this is the depth at which the light source is kept. So h is equal to depth at which light source is kept. Okay, so if you can find the value of r, we can easily find out the area of illumination, isn't it? So we can say that tan theta c from this triangle, so let me name the triangle, let this be a, this point be b, and this point be c. Then we can say from triangle ABC that tan theta c is equal to r by base is h. Okay, so tan theta c is r by h. So we know the value of tan theta c from here. Okay, so we can say that r is equal to h tan theta c, which can be written as h by square root of mu square minus 1. So you need to remember this formula, that r, that radius of illumination, is h by square root of mu square minus 1. Because if you remember this formula, you can find the area. Therefore area of illumination is equal to pi r square, and the value of r we can find out from this formula. Now the question will be like this, that a light source is kept at a depth of suppose 10 centimeter or 10 meter, anything can be given. So they will give you the value of h and they will tell you to find out the area of illumination, and they will not give you the value of r, but they will give you the refractive index of this liquid. Okay, so if you know the refractive index of the liquid, look into this formula, and you know the depth at which the source is kept, then we can easily find out r. If you can easily find out r, then you can easily find out the area of illumination by using the formula pi r square. I hope this much is clear. Okay, so this is how you need to use this concept and formula to find the area of illumination. So this is all about this concept. Okay, now let's look into one of the problem and then we will wrap up this video. Okay, now let's look into this final problem. It says complete the path of ray. Now if you just understand how the rays flow here, then many questions can be asked from this. So let's understand the concept first, then I will tell you what are the questions that you can get from this kind of scenario. Okay, now let's see. If this is the triangle given, that is this is 60 degree, 90 degree and this is 30 degree. Okay, and it says a ray of light is incident on one of the side at 90 degree, then what will be the path of the ray? Okay, so let's see. So we can see that if this is 90 degree, then this has to be 90 degree. Okay, if this is 90 degree, then this has to be 30 degree. Isn't it simple? Therefore we can see that is not 30 degree, but that is not the angle of incident. Angle of incident is always measured from the normal, isn't it? So this is the normal, therefore the angle of incident here on this interface is actually 60 degree. Okay, now you can see the critical angle is given to be 40 degree for the glass medium. This is actually a glass medium. Okay, and it's given the refractive index of the glass is 3/2. So since the incident angle is 60 degree, which is greater than the critical angle 42 degree, therefore it will undergo total internal reflection. Therefore we can see that this ray will move like this. Okay, and this angle will also be 60 degree because laws of reflection. Okay, now let's see what's happening. If this is the ray, then this will be the normal here, isn't it? Now let's see, if this is 60 degree, then this has to be 60 degree, therefore this will be 30 degree. Therefore the angle of incidence on this interface is actually 30 degree, not 60 degree. Don't confuse. Okay, now since the angle of incidence on this surface is 30 degree and we know the critical angle for the glass is 42 degree, so we can clearly see that the angle of incidence is smaller than the critical angle. Therefore this will not undergo total internal reflection, it will undergo refraction. So the rays will move like this, isn't it? Because we know the air is optically rarer medium, therefore it will move away from the normal. So what will be this angle of refraction? Okay, very easy, use Snell's law. So from Snell's law we know that, so let's use Snell's law, simple as that. And I have told the easier way of writing Snell's law is write down the refractive index of the glass medium, and the angle formed in the glass medium is sine 30 degree. Then the refractive index of the air medium multiplied by the angle formed in the air, that is sine r. Done. Now mu g is given as 3/2 and sine 30 is half and mu of air is 1. Therefore r can be easily found out like 3/4 sine inverse. Okay, this is what refractive angle is. Simple as that. So this is the path of the ray. Okay, now many questions can be asked on this, like how many times the ray will undergo total internal reflection? Your answer will be 1. Okay, you need to draw the ray diagram and check. By chance, if this angle was greater than 42, then again there would have been total internal reflection, and in that case the answer would have been the number of total internal reflection will be 2. Okay, in this case the number of total internal reflection is 1. Okay, so that could be our first question, that how many number of total internal reflection takes place. Another question that they can ask is at what angle with the normal the ray comes out of the prism. Okay, so you can find out the value of r and then that will be the answer. Okay, so these are the questions that can be asked based on this. I hope the concept is clear. The main thing that you need to understand is that don't be in a hurry and write this as the angle of incidence or this as the angle of incidence. Always calculate angle of incidence from the normal. Okay, this is a very important concept. This is all about the video. I hope you enjoyed this video and you got all the concept that has been spoken about in this video. Just understand one thing, if you understand the concept, then in NEET you can solve most of the question. Okay, so yeah, this is all for this video. If you enjoyed this video, then please give it a thumbs up, and if you haven't subscribed to this channel, then please consider doing so. Till next time, enjoy your studies and build your concept, and I will catch you all in my next video. Bye bye.